Okay, we're in section 6, homework. Again, I want to encourage you to do homework, certainly. There's only one way really to learn a material is to actually practice doing problems. So with that intent, to get you to practice problems, before you practice problems, you need to review what was covered in lecture and the notes and the examples problems we've done. And then this homework over here is something that you do on your own to see if you're capable of doing it. It shouldn't take long. If you understand the material that's presented to you, it really shouldn't take long to do. So let's take a look at problem number 1. And, one step at a time. I'm looking at a picture. It looks kind of crazy to me, but I do see the picture. This is an x-axis over here. This is the y-axis. And then I see some function being drawn over here. All right. So I want to see if I can answer the questions regarding this. All right. And as I do that, I'll put the work down that I believe is appropriate. So what it says over here, you're given a graph. I see the picture, figure 28, page 110. It says state whether the function in the figure is left continuous only, right continuous only, continuous, or neither at the following points. So let's put this down. And I'm going to write down A is x equals 1. If this is an exam question, this is the information I'll be writing down. X equals 1. First of all, what's f of 1? Well, you look at the picture, you find 1, and f of 1 would be the number 2 in appearance anyway. The next thing I would do is limit as x approaches 1 from the right of the function f of x. And I would do the limit as x approaches 1 from the left of f of x. Let's take a look at it. Again, this is the number 1. This is the right side of it. If I'm on the right side, it looks like I'm approaching the number 2. Let's go from the left side. This is the number 1. This is the left side of it. Looks like I'm approaching the number 3. So what am I going to say over here? Looking at it, certainly it's not continuous at 2, and clear as day, but it's right continuous. So how do I know that? This information here is telling me it's right continuous. I would recommend you look at the key and make sure they have written down. Got it. All right, let's go to the next one, which is B. And certainly I'll write down what B says. It says now x equals 3. So f of 3. This is 3. What's f of 3? It appears to be the number 1. I'm going to look at the limit. And again, this is just work. I'm writing it down. As we approach 3 from the right of f of x, and the limit as we approach 3 from the left of f of x. Should be relatively simple. Let's do one at a time. Again, this is 3, this is f, this is the right side. And kind of looking at it, let me just pull this down a little bit. I don't know, it's hard to read that, I'll be honest with you. So let me just make sure you know what I mean by this. This is the number 3 from the right, looking at it. I don't know, I'm going to say about 4.5. Let's do 3 from the left. It's over here. And I'm looking at it. Yeah, it's hard to read, but I'm going to say about, I don't know, maybe 2.5. All right. Again, if you can't remember the question, just read it. And I'm looking at it. It's clearly neither. All right. Clearly neither. Although the functions defined here, neither the right or left limit agree with the function's value there. So let's take a look, see if they said that. And they did. All right. Let's look at the next one. Next one says 5, right? So this is going to be C, x equals 5. And f of 5, I'm getting a little better at this, so I'm going to write this down pretty quickly. X goes to 5 from the right of f of x, and the limit x goes to 5 from the left f of x. I'm going to look at my picture, and let's see what's its value at 5. Again, it's hard to really know for sure, but look at this is 5. I have to trace over. I don't know. I'd say like maybe 1.4, I'll say. All right, let me do that for you. Whoops, I get my pen out, right? Let's do left and right. I kind of look at it, and we're doing 5, right? So left would be Well, 1.4. What's right? Let's look at it. Oh, by the way, I realized when I move things around, all my text didn't go together. So I'm just going to start to erase the old stuff. Sorry about that. Happens sometimes. So 1.4, I'm sorry, 5 from the right. I'm looking at it, and I'm going to say it looks about 3.9. What do I know about it? Well, these things are matching up, so it's left continuous. Again, I want to get my little pen out, see how we did, and we got it. All right, let's do number 2 now. And what's number 2? It says let the function be this over here. They say determine the value of f of 3. Well, that should be relatively simple to do. So this is number 2 and letter A. And what's f of 3? Well, looking at it, oh, I can't do f of 3 because it's not in the function. But what they go to say, how could you do it so f3 is left continuous at this? So what I would do is I would need to write down the limit as x approaches 3 from the left of the function f of x. And I'm looking at it. And which one of these two would allow that for me? So from the left would have to be this one over here. So it would have to be the number 4 in the limit, right? So what's f of 3? 4. So the answer is going to be 4. Look at it. What do they say? They say if f is left continuous at x equals 3, then f of 3 equals a limit. Well, I'm writing the information down, and they do clearly state it's 4. Write that over there. All right. So we did okay. All right. Let's go to B. All right, B down for you. This is determine the value. Oh, right continuous now. So f of 3 equals, I don't know, limit x goes to 3 from the right of f of x. Well, I got to look at this over here. This is the one that allows me to approach it from the right. What would that be? It would have to be minus 1 in the limit. So how's f of 3 going to be, should be defined as minus 1. Look at this over here. To the next page, I'll just go to that. I want to make sure it does say minus 1. And lo and behold, it does say minus 1. All right. So let's do number 3. It says use the laws of continuity to determine whether the function is continuous or discontinuous. Well, what do I have? I basically I'm adding a line to a trig function, and both of those functions are continuous on their domains. So this whole thing is continuous on the domain. All right. Let me just read this to you to make sure it's written down for you. So it says since x, what I say, it's a multiple of x, it's 3x. I'm just going to outline what they're saying. And cosine x are continuous. And again, 5 times cosine is going to be continuous as well. Then it goes on and says 3x and 5 times cosine x are continuous as well. Thus, the combination of them, the addition, will be continuous on the continuity laws. All right. Let's look at number 4. Number 4 says use law of continuity to determine whether function is continuous or discontinuous. What am I seeing? I'm seeing a ratio of problems. And what do I know about it? Again, what I'm noticing about it's a ratio. And certainly, 3 is a nice number. And this is a nice thing over here. I want to point out that 3x squared, whoops, sorry about that. 3x squared plus 4 never equals 0. So this thing is defined for all real numbers. So it's continuous on its domain. And what's its domain? It's a rational function, minus infinity to infinity. That's the domain of it. And it's a rational function. Rational functions are continuous on the domain. So where's this function continuous? Everywhere. All right, that's done. Let's go to number 5, a little more difficult. And number 5 is, we have a ratio here. 3 to the x is always continuous, but I got to worry about the bottom. And these are exponential functions. Does the bottom ever take on a 0? Well, this harkens back to my Math 119 days, and I got to solve this thing. This is 4x equals 9. And by the way, I'm writing down this guy's domain now. I know it's all real numbers except some number can't come in. And what would this be? I would take the natural log of both sides, and you would get x ln 4 equals ln 9. This is what you learned in Math 119. And x would equal ln 9 over ln 4. So I'm going to say it's all real numbers except ln 9 over ln 4. So I'm going to say the function continues on its domain. Well, what's its domain? Its domain is all real numbers except ln9 over ln4. So it goes on to say the function has a infinite discontinuity at x equals the natural log of 3 over 4. Oh, they wrote a different thing down. Let me write that down. I don't know where that came from. Did I write it? Oh, I see what I did wrong. I wrote the wrong number down. And I have to correct myself. I put a 9 here when it should be a what? A 3. I got to erase all this nonsense over here. Happens to me sometimes, but again, it's good it happens because what it gives me opportunity to correct myself. So -3 equals 0. And this would be, just going, it's 4x equals 3. Take the log of both sides, and you get the natural log of 3, natural log of 4, would I divide both sides by that eventually. So x not equal ln3 over ln4. And I'm sure you realize the bottom would become 0, and this thing's going to have a blow up. But that's why I say infinite discontinuity there. So it's continuous on its domain. What's its domain? All real numbers except the natural log of 3 over natural log of 4. And that's clearly stated over here. All right, students of 19, especially if they do not know how to solve that equation. Yeah, continuous on its domain. Whoops, sorry about that. What's its domain? Its domain is this business over here. Let me write down an interval notation for you, though. And if I write that in interval notation, that's going to be minus infinity up to the natural log of 3 divided by the natural log of 4. Union starts up again, natural log of 3 over natural log of 4 off to infinity. That's the domain of it. I think it's easier just to write down all the real numbers. X cannot be natural log of 3 over the natural log of 4. That's where the function is continuous. All right. So this one over here, determine the points which a function is discontinuous. This is fairly easy. Its domain, I'll write it over here, is going to be all real numbers except x equals 3, right? So it can't be 3. So we're discontinuous at 3. It's discontinuous over there. It goes on to say, you tell me what kind of discontinuity that is. Well, in 119, you actually graph these guys out. And what you should know is there's an asymptote, and that asymptote would be x equals 3. And what do you know? To the right of 3, the function would go to plus infinity. And you learn this in Math 119, and this would be going to minus infinity. So what kind of discontinuity? It's infinite, right? It's infinite. This infinite written over here, it says x equals 3, infinite discontinuity. All right, let's look at the next one. It says determine the points at which a function is discontinuous. Well, I got to write this down now. It's going to be equal. This is 2. It's a rational function. And you get t minus 3. So what's its domain? Its domain is all real numbers, but the t cannot be 0 and the t can't be 3. All right, so what do I know? I got asymptotes there. We learned this in 119. And this is t equals 0 and t equals 3. So I'm going to point out what happens over here. And this is something, again, you learn in Math 119. Some of your teachers said use sign analysis. Well, I'll do that. If you took a 4, what would you get? Well, on the bottom, and this is sign analysis, you'd get a positive number, so plus infinity. Now, if you took a number below 3 but above 0, like I'm going to say 1, plugged it in, it would be negative. Right, asymptotes. All right, not so bad. If you took a number below 0, like -1, you would get a positive. So what I'm saying over here, I can do the limits for this guy over here, which you did in 119. So I'm going to say it's discontinuous at 0 and at 3, and they're infinite. All right, so they're infinite. Let's go to the next page. Make sure it says 0 and 3 and infinite. And where they say infinite discontinuities at 3 and 0. So I feel pretty good about that. All right, so next question number 8 says, is the following statement true or false? It goes on to say, f of x equals, 2x to the 3s minus 7x cubed is right continuous at 0. Well, let me write this down. So f of x, and again, this requires a little bit of work, not much. I'm going to write this as, x cubed. And by the way, don't feel obligated to do so. Square root of x, all right? Minus 7x cubed. So the domain of this problem over here is going to be, the x has to be greater than or equal to 0. So the domain is 0 to infinity. All right. So I'm going to write down f of 0. And f of 0 would be what? It would be 0. That's pretty simple. Now, what I got to do is I got to do the limit now. And the limit, the only limit I can do is x goes towards 0. All right, from what side? Well, again, we're encouraging you to look. And this is what you're looking at over here. It can only come from the right side. I'll put this down for you. Of the function f of x. Well, that's pretty easy. What do you get over there? 0. So what do I know? I know it's right continuous. I would look at the work, see what they say. They said the function is defined at x equals 0, and the limit as x approaches 0 from the right of f of x is also equals 0. So I feel good about that. All right, number 9. And again, I'm reading the questions as we go through. It's pretty quick to do. It says determine the points at which the function f of x is discontinuous. And I'm going to look at it, and I don't know. I'm going to say, looking at it, the f of x is piecewise. The second one says if x equals if x equals 3, it's equal to -9. And then the first function says the absolute value of x minus 3 on bottom and top is x minus 3, provided x isn't 3. So I'm going to say it seems like something's going on at 3. All right. So I'm going to say the first function is certainly continuous everywhere except at 3. Well, I got that written down. The second function, you just simply -9, and that's at x equals 3, just a single point. So that's fine. So what I'm going to look at, I'm going to look at this is number 9, by the way. I'll write this down. So I have some suspicion at 3, something's going on at 3. So let's put this down, f of 3. And what's that going to be? Well, let's take a look at that. F of 3 is going to be -9. And then I'm going to look at limit as x approaches 3 from the right of f of x. This might be tough, right? And the limit as x approaches 3 from the left f of x. All right. I got troubles. I'll tell you what the troubles are. Well, to the right of 3, and let me make sure I write this down for you. The absolute value of x minus 3 is equal to x minus 3 if x minus 3 is greater than or equal to 0, and it would equal the opposite, which would be minus x plus 3 if x minus 3 was below 0. All right. So I'm hoping that's not throwing you for a loop, but it could. A lot of students, they look at that and say, I don't even know why you bother writing that down. Well, I have to write that down for a reason, because I need to think. And part of my thinking is writing things down and communicating too. I want to communicate with you. So I'm going to keep rewriting this guy over here. And I'm going to write this down over here. And this is going to be equal to x minus 3 if the x is greater than 3. And it would be minus x plus 3 if the x was below 3. So I'm looking at it, and I want to write down the function now, but I have to do the limit. And this gets really confusing to a lot of people. 3 from the right. Well, this is the only one that will allow me to write down 3 from the right, and that would be equal to x minus 3. What's equal to x minus 3? The bottom, which is x minus 3. All right. I'll write that down for you. Well, that limit couldn't get any easier. And the reason for that is these things cancel off. Again, x is not 3, so there would just be, some non-zero number, but identical on top and bottom. And what's the limit of that going to be? Just simply 1. I got that covered. Let's do the next one. Limit x goes to 3 from the left. The top is still x minus 3, but what's the bottom? And again, I want to point it out to you. The bottom is the absolute value of x minus 3, but for the left side, and this is the only number here that would let me approach it from the left side of 3. So it's going to be minus x plus 3. It's sort of like what you did in Math 100. The top and bottom are opposites, and what we give here, limit x goes to 3 from the left. That means it's not going to touch 3, and this thing would reduce to -1. What's that limit? -1. So what do I know? It's not right continuous. It's not left continuous, because -9 is not matching either 1 or -1. But what kind? I'm going to say it's discontinuous. So it's discontinuous. But what kind of discontinuity do you have? It's a jump. So it jumps from -9 to 1 or -1. It jumps around. All right, let's take a look at the blue area. I'll read it to you. It says x equals 3 is jump discontinuity. You should look at the limits. We did do that. from both the left and right. We did do that, and the function's value at x equals 3 to see this. A graph may also prove to be helpful. Now, I realize for a lot of students, graphing is not helpful because they can't graph, all right? Oops, sorry about that. So I'm going to claim over here, I'm going to put a graph down, all right? Let's write this over here. F of x, oh, damn, I did it again. F of x equals, well, the function x minus 3 over absolute value x minus 3 for x not 3, and then minus 9 when x is 3. I'm going to graph this here. And again, I'm not saying it's easy for you. We're trying to encourage it. Maybe a graph might be helpful. So at 3, 1, 2, 3, you would get minus 9. I'll put this over here. That's a nice big dot there. All right. Now, when you're above 3, do you remember that? What does the function really look like? 1. I'll put that down. And what's that going to look like? Look like this over here. When you're above the 3. When you're below the 3, what does it look like? It looks like minus 1. All right. Clearly seeing the function's defined at 3, but it actually jumps. It's jumping around. Okay. You clearly see a jump in that. I hope you do. All right, let's take a look at this one over here. And number 10. And it goes on to say, determine the point at which the function f of x is discontinuous. And kind of looking at it, I'm going to say, there's trouble here. And the trouble would be at the value 4. Right, so I'm going to write this down. So number 10, I'm going to write down number 10, f of 4 is equal to 0. But now I got to write my limits down, and limit, and I know this is difficult. A lot of students are going to shut down at this point, saying they just want to make a guess at it. Guessing is not a good idea. Where are we going? 4 from the right of f of x, and we're doing limit 4 from the left of f of x. And what I want to do is I just want to look at it. And I don't want to do a lot of work, but I hope you realize if we're 4 from the left, right. What would you get over here? It's a sine function, which is bouncing around a lot, right? Between plus or minus 1. But what would you get over here? You would get 1 divided by, well, if you plug in 4, you get 0. But the right side of it, it's really not 0. It's a positive number. It's above the 0. So this goes towards plus infinity. And what does the sine function do towards plus infinity? It bobs up and down between plus or minus 1. So I'd say that this over here is d and e. And what do you get over here? Let's take a look at it. Again, I was going to look at it. When you're at the left of 4, right? What does that mean? Numbers smaller than 4. Well, this goes towards 0 on the bottom, but through negative numbers. So this would be minus infinity. And what's sine of minus infinity? Again, it bobs up and down between plus or minus 1. So it's another d and e. So I'm going to read it to you. What does it say? It says classify this as removable. Well, it's not removable. I can't remove that. It's not jump. What is it doing? It's oscillatory. It's going back and forth between two numbers. What number is going back and forth between minus 1 and 1? It includes all the numbers in between that. So it oscillates between the two. All right. So I'm going to say it's oscillatory. Let me write this down for you. I see that here at 4. It goes on to say a graph may be helpful. The problem with graphing these things over here is when you do graph it, you're going to find out that the thing gets very dense when you get near 4. It is basically bouncing around between plus or minus 1. So let me just point out by that in a graph. And again, I'm not saying it's going to be easy for you, but you may want to use technology to do that. And I'm going to point out at 4 over here, what you're going to see is, certainly if I graph that out, you would have a point here. But what happens to the left and right of it, as the function comes in, it's going to be doing this over here, going back and forth between plus or minus 4. and it's going to top out at 1 and bottom out at -1. And you can try that in a graphic utility. It's just really hard for me to graph it out because it does oscillate very, very quickly. Here's your deal though. For as far as learning though, it's really important you start thinking about that. You start thinking about what oscillations mean when you get close to a number 4. It gets really dense. And if you zoom into this thing over here, it's going to just look like completely filled in space because the thing is really bouncing around incredibly quickly. All right, let's take a look at number 11, a little more difficult. I'm seeing the exponentials in bottom. And what's they classified as jump? Oh, I have to deal with this. So before I deal with this, what I got to do is I got to figure out when the bottom is equal to 0. And this might take some effort, but I want to claim to you, it should never take too much effort that you can't do it. So when does the bottom become 0? When either 2x is equal to e to the minus x plus 3. And this could only happen if 2x is equal to minus x plus 3. And what do you get over there? Well, 3x is equal to 3, x would equal to 1. So I'm going to say I'm really interested in what happens at 1. So what do I get over here? I get f of 1. What's f of 1? It's undefined. That's the only place. So what I want to do, I want to look at the limit of it, right? So determine the points at which the function is discontinuous. I am definitely going to say at x equals 1. So the domain of this guy over here, we're talking about this function over here, is all the real numbers except you can't have 1. But what I'd like to do is I'd like to look at, what's happening at 1. And so I'll put this down for you. Limit as x approaches 1 from the right of f of x. I'm going to write the f of x down this time. It's 4 e to the 2x minus e to the minus x plus 3. And granted, I know this is difficult. We're trying to encourage you to think. Get my eraser out. I'll erase this business over here. No, do not erase your work on exams, by the way. I got to think about it, all right? I really do. Problem with thinking you could be wrong. All right. Let me just point out what I'm doing over here. 1 from the right side. All right. So I got to start thinking about it. And really what I'm thinking about is I'm thinking about the bottom number, which is e to the 2x minus e. I'm going to write down 3 minus x. All right. I got to start thinking now. So I'm going to say this is e to some number that's bigger than 2. Now, how do I know that? If I'm on the right side, the numbers are bigger than 1, and 2 times a number bigger than 1 is bigger than 2. And what do I get here? Minus, whoops. All right, sorry about that. Minus e, well, 3 minus 1 is 2. Right, would you agree with that? But here's the deal. X is bigger than 1. So 3 minus a number bigger than 1 is going to be smaller than 2. So I hope you realize that, roughly speaking, they're going to be the same number. It's definitely going towards 0. But what kind of a 0 is it? So if you look at this over here, this number is going to be bigger than this number. So it's 0 from the right side. So this will be plus infinity. I know that's tough. Let's do the other one. Let's do left side. This is left. I'm just looking at the bottom. Let me cross this out. I'm done thinking. So from the left of 2, this will be e 2 smaller than it. Now, why do I say that? If you're to the left of 1, like, 0.9, 0.99, well, 2 times that is always going to be smaller than 2. Let's do the next one. Minus, well, you know what? I noticed I just copied something wrong. This over here, I got to correct that. All right, get my eraser out. Sorry about that. So I'll put this over here. So it's going to be E, and it's going to be 3 minus a number smaller than 1. So it's going to get close to 2, but it'll certainly be bigger than 2. So what do I know about that? The bottom would definitely be 0. Those numbers are relatively the same. But the second guy overpowers the first guy, so it's going to be negative. What do you get over there? Minus infinity. All right. So I know this function is discontinuous. And what kind of discontinuity is it? It's a discontinuity at 1, and it's called an infinite discontinuity. Let's look at our answer key. Okay. Students may need to review Math 119, especially if they do not know how to solve a very simple equation. It's true. You have to review 119. Now, granted, let me just repeat this. What happens to a lot of students is that although they've taken 119, they weren't terribly engaged in their studies. And this builds up over time. It becomes almost like nonsense. That's almost like if you don't, basics of language, that also when someone starts to talk, everything becomes nonsense to you. Well, if you don't know the basics of mathematics, like what you learn in algebra or pre-calculus, this calculus stuff really becomes a bunch of nonsense for you. And we're trying to prevent that from occurring, including you have to go back and maybe retake or redo a class. And we have plenty of resources online for you to do that. We don't have to spend money on it. All right, let's go to 12. Get a little better at this. Determine the domain of this guy here. Couldn't be easier. It's a 119 question. So I'm going to put that down for you. This is an even root. So the radicand must be greater than or equal to 0. And let me go through the work with you. It's an easy question. I'm glad for easy questions. So number 12, I got to write down, whoa, I keep doing that, don't I? 3x squared minus 27 greater than or equal to 0. You study this in Math 119, by the way. So I got to factor it. A 3 comes out. You get x squared minus 9. And this is so typical. We write problems that work really nicely for you. So x plus 3, x minus 3 equals 0. Put a number line down. Just doing what you did in 119. There's 2 zeros, minus 3 and 3. I would take a test value. Like between minus 3 and 3, a good test value would be 0. Plug it in. What do you get? Positive, positive, negative. So in that interval, it's definitely negative. If you took a test value after 3, like 4, plug it in, positive, 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 everything turns out to be positive. If you took a test value below minus 3, like minus 4, what do you get? Positive. This would be negative, and this would be negative. A positive times a negative, of course, is a positive. What's the question now? Well, let's look at it and point it out to you. The question is this: when is it greater than or equal to 0? Well, I know when it's greater than that. It's greater than that when it's positive. So over here and over here. I know that much. The other question is when equal to 0. Well, if you plugged in minus 3, that would be good, and 3 would be good. So what's the domain over here? I'll look at my number line. I'll write this down for you. Minus infinity up to minus 3. That's on the right side, and it's included. Union 3 to infinity. All right. Do they put that down for an answer? Yes. What does it claim that you need to do? You may need to relearn Math 119. And let me repeat this. If you don't understand Math 119 or 120 or Math 100, at least the way it's presented at Essex County College, you're going to have a tough time with calculus. And we're not looking forward to that, by the way. We really aren't. All right. Another number 13, a little more difficult. It's a domain problem. But what do I know about this thing? Well, a couple things. One thing I know for sure. I know that x to the 1/2, again, we're doing problem number 13 now. I know x to the 1/2 is basically just a square root function. All right. So I know that this thing here, square root function. So I know the x must be greater than or equal to 0. The other problem I've got is I wonder, when does 5x minus x to the 1/2 equal 0? I don't know. I got to figure that out. The way I would do that is I probably would do this over here. And then I'd square both sides. I would get 25x squared is equal to x. Then I get 25x squared minus x equals 0. I'd factor an x out. And what do you get? You get 25x minus 1 equals 0. And I'm ready to write it down now. And what is it going to be? Well, x equals 0 would be solution to that. And x equals, well, it's going to give you 1 over 25, right? So what do I have? Well, and again, I hope you can remember. I know the x must be greater than equal to 0. But now I also know it can't be these numbers here. And why is that? there'd be a division by 0. So the domain, ready for this? X must be greater than 0. I can't include that. Remember that. You can't include that. I'm looking at this, by the way. So I can't include the 0 now. And X can't be 1 over 25. Let me write down interval notations. 0 up to 1 over 25. Don't touch that. Union, start up again. 1 over 25, don't touch that, off to infinity. That's the domain of it. I'm going to look at the K, see if we got it right. Someone says, why do you need to do that? It's not me needing to do that. You need to do that. And it's right over here. All right, that's the domain of the problem. Let's look at 14. Relatively simple question. I think I can do this pretty quickly. I'll write it down for you. What am I seeing? I'm seeing a function. It's divided in pieces. When did you first see piecewise functions? In Math 119. It's so important you have that background. 2 from the right. I'll write this one down for you. This will be the limit as x goes to 2 from the right. Of these two functions, which allows you to go for 2 from the right? This one. So it would have to be 4 minus x. Relatively simple limit to take. What do you get over there? 4 minus 2, which is 2. Let's do the next one, and we'll check the key in a second. X goes 2 from the left. Which one of these two functions here? Let's go for 2 from the left. This one. So it's 3x squared. Relatively simple limit. What do you get over there? 3 times 4, which is 12. Let's get our answer key, see how we did. And we got the work done. That's great. All right, determine what the function is, right continuous, left continuous, or neither. Oh, let's do that. So what do I got to do? I got to write down f of 2 now. All right, which one of these two functions lets you touch the 2? Only this one. So what's f of 2? 3 times 4, which is 12. I want to point this out to you. This is matching this. So what is it? It's left continuous. Go to the next thing, which will hopefully be number 15. Okay, same story. It says, let f be this function over here. Find the value c that makes the function continuous everywhere. Let's write this down. And it's going to be work to write things down. I want to encourage you to do work. I'm going to do f of 4. I get better by working, by the way. This is the only one that let me touch 4. So what are you going to get? Well, if x is 4, that's 24 plus 4c. Then I got to write my limits down. Limit as x approaches 4 from the right. And I have to write the limit as x approaches 4 from the left. All right, so let's take a look at it. So 4 from the right, which one of those two functions? It's got to be this one over here. So write that down for you. What do you get? 6x plus 4c. And what does that equal? 24 plus 4c. All right, let's do the one from the left. This is the only one that lets you approach 4 from the left. And what is it? X squared minus c. All right, what does this give us? Well, 16 minus c. Now, what do I know? If it's continuous at that, what do I know? Everything's got to be equal. So these two limits have to be identical. Let's write that down. 24 plus 4c has to be 16 minus c. Let's go through it. What I would do probably, I don't know, I probably would subtract, I'm not going to add c to both sides, 5c, and I would subtract 24 from both sides, and that would be minus 8. Did I do that right? If I add c, I get 4, yeah, 5c, subtract 24, yep, minus 8. So what's c? C would be minus 8, this. All right, let me go back and see if I read the question. Let f be a function. Find a value of c that makes the function continuous everywhere. Well, we just did that. The value of c would have to be minus 8 fifths. Let's look at the answer key, see if they wrote that down. They did. They also wrote the limits down for us. Those limits would be equal at minus 8 fifths for c. All right, let's look at number 16. And number 16, basically, you know, I'm looking at a limit problem. And I want to get across to you that a lot of this stuff is intuitive. We're not really writing down, you know, that this epsilon delta thing for doing the limit problems, but it can get tough. And a lot of it's really based on your knowledge and prior learning experiences. And I hope you know that e to the x, whoops, sorry about that. E to the x is basically continuous everywhere. It looks sort of like this over here. All right. So let me just erase that. And I hope you know that arctangent is a function that looks like this over here. And that's also continuous everywhere. And that's good to know. All right. So I'm going to say it's something to do with continuity. And I'm going to start to, maybe go backwards on it. And let me see if I can get rid of that graph there. And I'm going to look at this one over here. And I want to be careful about it. And I'm going to look at it. And what I'm going to look at, I'm going to look at the limit of the inside first. All right. So it's going to be 6 arc tan limit as x goes towards 0 e to the x. Well, that looks pretty simple to me, because if you go towards 0 for e to the x, with the left or right, it's going to go towards the number 1. So what do I get? 6 arc tan of 1. All right. Now someone says, I don't remember anything from Math 120. Well, you should. You should know how to take the arctangent of 1. And what's that going to be? Pi over 4. And what do you get there? I got to reduce it. I'm going to say by 2. So 3 pi over 2. Look at your key. Make sure you're staring at that. All right, let's go to the next page. And, well, some people, they don't like these because they have to write. All right. I'm going to read through it. All right. So it says, which of the following quantities would be represented by a continuous function of time, and which would have one or more discontinuities. By the way, I'm going to say, looking at letter A, they're relatively simple. The velocity of an airplane. I hope you know the velocity of an airplane, it's smooth, right? It's really a very continuous. If you look at the speedometer, it's very continuous flow of motion. So let's just read it. It says the velocity of an airplane during flight from Boston to Chicago is a function of time. Let me read that question again. Which of the following quantities would represent a continuous function of time? Yeah. So they're asking, yeah. So I put an example down of a flight from Boston to Chicago. You don't have to do that, by the way, but it's certainly a continuous function of time. How about temperature in the room? I would say yes, it's also a function of time, right? So the temperature in a room is a function of time. It goes up and it's continuous. It goes up smoothly and it goes down smoothly. I would say ordinary conditions. All right. I can't imagine, something, nuclear war maybe or something, but I don't even think that would be that rapid of a change. Okay. The value of a bank account with interest paid yearly. This definitely gets jumped. What do I mean by that? There's sort of like a constant number, and all of a sudden, at the moment they compute the interest, the balance is going to jump. So let me read that to you. The value of a bank account interest paid yearly is not continuous. It jumps up. What is a discount when deposit or withdrawals are made and when interest is paid. Seems like reasonable. How about the salary of a teacher? Well, I hate to say that, I hate to talk about personal experiences, but my salary, for the most part, at least over time, hasn't really changed. All right. No raises. Actually, it has changed. It's gone down. They actually dinged us. All right. They took a pay cut. All right. So I'm going to say over time, though, most teachers' salaries, when they got a pay cut, all of a sudden, boom, it shoots down. Not a lot, by the way, but it shoots down. Likewise, when they get a pay raise, it shoots up. It actually jumps either up if they get a raise or down if they get dinged. People get dinged a lot nowadays. But anyway, the salary of teacher is not a continuous function of time. It is down to when the teacher gets a raise or whenever his salary is lowered. All right. Let's look at the population of the world. I got to be honest with you. Most people can treat this as a continuous process. The reason being is the numbers are so huge. We model it using a continuous thing. But you should realize that there's some subtlety going on here. The population changes at integer values. It really does. But we do treat it as a continuous problem. Anyway, let's read it. The population of Western world is not a continuous function of time since it changes by a discrete amount with each birth or death. And that's true. However, since it takes on a very large number, it's in the many billions, and it's almost embarrassing how many people are on Earth at this point. It's often treated as a continuous function, and it is modeled using a continuous model. If you have a smaller population, it's going to be discrete. All right, it'll be discrete. All right, so there's a connection. Sometimes it's not kind of obvious. Some people say the world is nothing but a discrete function. Everything in it is discrete, but we model mostly with continuous functions. We really like that. All right, so that covers that. I know it's a long section of the notes, but it's done. Thank you for paying attention.